At this moment, while these words unfold, an immense cloud of magnetized plasma is moving through the 93 million miles that separate the Sun from Earth. Its mass is on the order of 1 billion tons, and it is expected to reach us tomorrow afternoon. The agency responsible for watching the Sun has already released an official warning. A strong geomagnetic storm is on the way. If the weather above you is clear, the result may be a rare and haunting sight, with the northern lights drawn far south into regions where they are almost never seen. It should be beautiful. It should also be something we can endure. Yet the quiet truth behind those glowing curtains is easy to miss. The same force that spreads color across the night sky is also the most serious natural hazard facing the technological world we have built. Tomorrow's event is only a smaller expression of that power. A much larger expression has happened before, and it only narrowly failed to strike us. If this is the kind of solar story you want to understand before it becomes a headline, follow Calm Space, where the Sun is watched through quiet weeks and dangerous ones alike. And if you plan to look for auroras tomorrow night, the light may feel different once you understand what is behind it. So let us begin with the watch, somewhere across the northern half of the United States tomorrow night. Under a dark enough sky, and away from the haze of city lights, people may glance north and see the atmosphere doing something it rarely does there. A green glow may stretch low along the horizon. A faint red veil may hover above it. It may ripple gently, almost silently, in a sky that usually remains dark. Cars may stop at the roadside. Phones may rise toward the heavens. And for many of those watching, the moment will seem only magical, not dangerous. That is part of what makes space weather so strange. The warning sign can arrive as beauty. The force that draws those colors through the upper atmosphere is the same invisible disturbance now approaching Earth, only at a level expected to remain survivable. The alert has already been issued, and it is not casual speculation. This is not a loose guess or a vague forecast made to fill a quiet day. It is a formal, numbered alert from the office, whose purpose is to monitor the Sun and its effects on Earth. The forecast calls for a geomagnetic storm rated strong on the official scale, with arrival expected tomorrow. The material responsible is no longer waiting on the solar surface, undecided. It has erupted. It is traveling now. A vast cloud of magnetized solar matter, larger in scale than the planet in its path, is crossing the distance from the star that sustains us to the world that depends on it. Its arrival is expected around the middle of the day tomorrow. The wording of the warning matters, because space weather is often hidden behind technical language until it is already affecting systems. The alert comes from the Space Weather Prediction Center, the United States government office that plays for the Sun, a role somewhat like the Hurricane Center plays for tropical storms. Its task is constant vigilance, hour after hour, day after day. It watches the solar environment and issues alerts when conditions become concerning. In this case, the term used is a watch, the same kind of word familiar from terrestrial weather, when conditions are beginning to align for something hazardous. 2 days ago, that watch was issued, Geomagnetic Storm Watch Category 3, labeled in plain language as strong. With this new notice, earlier watches were replaced. The message became simpler and more direct. Tomorrow, the strong storm arrives. Attached to that forecast is the number 7. This number belongs to an index used to describe how severely Earth's magnetic field is being disturbed. The scale begins at 0, where conditions are quiet, and reaches 9 at its upper end, where the most intense historical storms are found. For the period extending through the late afternoon and evening in universal time, the forecast places the index at 7. That is not an ordinary value. A 7 is high enough to pull auroras out of their usual Arctic setting and send them into the skies above the northern tier of states, and perhaps even farther. It is also the kind of value that draws close attention from satellite operators and from those responsible for monitoring the power grid. In a calm documentary sense, This is where the story becomes larger than a night of skywatching. The number is a doorway into the scale of what the sun can do. Hold on to this distinction, because it is the central thread. A 7 is serious, but it is also manageable within the broader range of solar behavior. The lights will very likely remain on. Phones should continue to function. For most people, the auroras will be the main story, and a day later the event may already be fading from memory. That needs to be said plainly, because a strong storm should not be turned into something it is not. Calm space does not need to manufacture fear from an event expected to be mostly survivable. Still, the process arriving tomorrow is not separate from the process behind the worst possible solar disaster. It is the same physics, expressed at a different scale. A cloud of charged particles leaves the sun, crosses interplanetary space, and collides with the magnetic bubble surrounding Earth. The planet's magnetic field responds. Electric currents are driven through the ground, and those currents can interact with the systems humans have connected to it. Tomorrow, that happens at a level forecast near 7. In a true catastrophe, the number would not stop there. It would push beyond the useful top of the scale. It would not pass harmlessly in a few hours. The lights might not stay on, satellites might not all make it through, recovery might no longer be counted in days. That is the uncomfortable comparison. Not that tomorrow is the disaster, but that tomorrow is made of the same ingredients. To feel the scale properly, consider what an index of 7 means. This measurement has a logarithmic character, so moving from 5 to 7 is not just a neat little step upward. It represents a major increase in how violently Earth's magnetic field is being shaken. On most days, the index may sit around 1 or 2, quiet enough to barely draw notice. Tomorrow's forecast raises that disturbance to several times that ordinary level. The storms that have caused real damage in the past, the ones that brought down grids and destroyed equipment, press toward the upper end of the scale, into the 8s and 9s. The most extreme events went beyond the scale people had available to describe them. Tomorrow is a strong shove. The catastrophe would be a sledgehammer. Yet both are delivered by the same solar mechanism, and that is why the event deserves careful attention rather than panic. The deeper story is not simply that a storm is coming. It is the space between two possibilities, a memorable night of auroras on one side, and a continent struggling in darkness on the other. Tomorrow may show us the gentle face of a force that, in another form, could test the foundations of the modern world. We know the smaller version of this story because we have experienced it again and again. During an active stretch of the sun, like the one unfolding now, Earth can receive these lesser blows every few months. A burst of radiation, a magnetic disturbance, perhaps auroras reaching farther south than usual. What modern civilization has not experienced, not during the entire century in which we have built an electrified, satellite-dependent, hyper-connected world, is the truly large version. That is the unsettling contrast at the heart of this subject. The same solar power that can paint the sky over Michigan with beautiful light can, if it arrives with enough strength and the wrong timing, threaten the power grid across half a country. A storm of this kind may be harmless spectacle at one scale and a civilizational hazard at another. So the real question is not whether the sun can disturb us. It is how large the disturbance is, how it is aimed, and what our infrastructure is prepared to endure. Tomorrow brings the smaller version. Tonight, we need to look at the larger one, and at the quiet way our way of life has become exquisitely vulnerable to a force we cannot switch off. To understand the storm expected tomorrow, we have to begin with the week that created it. The sun did not simply awaken 2 days ago and hurl material toward Earth. The pattern had been developing for much of the week. And the order of events matters because each one was a smaller preview of the danger we are tracing. Around the 2nd of June, a magnetically intense area on the visible face of the sun, numbered 4,456 by scientists, became highly active. In practical terms, it began erupting. In a single day, it produced 5 separate flares, one of them already large enough to command attention. Yet that first day was only the prelude. The revealing moment came on the 3rd of June, when the same region released 3 major flares within roughly 10 hours. Just after 1:00 inches the morning, universal time, it produced an M9.3 flare. Between about 4 and 7 inches the morning came another, rated M7.7. Then, late in the morning, a little after 11, the region fired the strongest of the sequence, an X10 flare. 3 significant eruptions from one location on the Sun, compressed into one morning, tells us something important about the energy stored there. It suggests not a calm surface with an occasional spark, but a magnetic system repeatedly finding ways to break. The flare labels can sound abstract unless we slow them down. Solar flares are classified by the amount of X-ray energy they release, moving upward through C, then M, then X, with each letter representing a 10-fold increase in power. A class flare is comparatively minor, the kind of event that can blend into the background during an active solar period. An M-class flare is 10 times stronger and can interfere with radio communications. An X-class flare is 10 times stronger again, the highest named category and the realm of the most powerful output. So, an M9.3 flare is not just another M flare. It sits at the upper edge of that class, almost touching X, a near X-class event in practical terms. Seen this way, the 3rd of June was not a morning with one serious flare and 2 afterthoughts. It was a rapid sequence of 3 major releases, 2 near the top of the M class and 1 fully in the X class, all from one magnetic region. That compressed timing is easy to overlook, but it is the detail that gives the episode its weight. Even when the Sun is active, a major flare is usually treated as a notable event, a marker in the day. To see 3 from the same area in a window of about 10 hours is the Sun operating at a pace it does not normally maintain. One might compare it to a fault line, producing not one major earthquake, but 3 from the same stretch of ground before the morning is over. Each eruption should relieve some of the stored strain, yet region 4456 kept gathering itself and firing again, implying that a great deal of magnetic energy remained packed into that twisted structure on the surface of our star. Why would a single region behave like that? The answer lies in its magnetic arrangement. The sunspot group responsible carried a classification written by specialists as beta-gamma-delta. The wording is technical, but the meaning is straightforward enough for this story. Its magnetic field was deeply tangled. North and south magnetic polarities were crowded together in a complicated, unstable pattern, twisted in ways the Sun cannot hold indefinitely. Imagine a rubber band being wound tighter and tighter. Eventually, the tension needs a release path. On the Sun, when a tangled magnetic field snaps and reconnects, it can pour out energy as a flare. At times, that release also throws part of the Sun's outer atmosphere into space. The most contorted regions, especially delta regions, are associated with the largest flares, and 4456 was an extreme example of that kind of magnetic complexity. This matters because the week did not remain a distant fireworks display. On the 5th of June, 2 days after the triple flare morning, Earth was struck by a real geomagnetic storm. It was rated G2 moderate, driven by plasma, launched during the earlier activity. The index used to track the disturbance of Earth's magnetic field rose above 6. In other words, this chain of events had already reached our planet once. It was not a model, not a distant possibility, not just a bright eruption seen from afar. The Sun had already delivered one blow. The storm forecast for tomorrow is the second, and it is expected to be stronger. That second blow was set in motion on the 6th of June when another flare occurred, this one rated M18. This time, The eruption was accompanied by something forecasters could observe as it left the sun: a partial halo coronal mass ejection. A coronal mass ejection, or CME, is the part of the event that matters most for geomagnetic storms at Earth. It is not merely light crossing space. It is matter, a billion-ton cloud of magnetized plasma blasted from the sun's outer atmosphere and sent outward into the solar system. When such a cloud is directed at least partly toward Earth, it can appear in coronagraph images as a halo, a spreading ring around the sun, because the material is moving more or less toward the observing instrument and therefore more or less toward us. The eruption also revealed its speed through a Type 2 radio sweep, a radio signature produced by a shockwave moving through the sun's atmosphere. From that signal, its speed was measured at around 838 kilometers per second, more than 1,012 miles per hour. Along with it, an 11-degree long filament of solar material erupted as well. Taken together, these details do not require drama to feel significant. They simply show a restless sun releasing energy in stages, and they leave us with the quiet question that matters most. When the next cloud arrives, how much of its magnetic force will Earth have to absorb? Held above the solar surface was a vast filament, cooler, heavier gas, suspended in the sun's atmosphere by magnetic fields until those fields released their grip and threw the structure outward. The cloud that left on the 6th is the one expected to arrive tomorrow, in the middle of the 8th. It is useful to slow down here, because the term coronal mass ejection sounds almost tidy, while the event itself is anything but small. When the sun produces one, it is not merely breathing out a little gas into space. It can launch a magnetic structure containing 1 billion tons of matter. By the time that expanding cloud reaches our region of the solar system, it may have spread to a width many times greater than the distance from the Earth to the Moon. It grows as it travels, becoming large enough in scale to engulf Earth and its magnetosphere, with space left around them. Yet this is not a solid wall racing toward us. Its material is stretched across such an enormous volume that any individual part of it is extremely thin. The real concern is not density in the ordinary sense, it is magnetism. The cloud carries its own magnetic field, and when that field sweeps across Earth, it can disturb our planet's magnetic shield and set the rest of the storm in motion. So the picture is strangely delicate and immense at once. 1 billion tons of magnetized plasma, moving at over 1 million miles an hour, expanding until our world looks small inside its reach. And after tracking it across space, forecasters must still wait for one crucial detail: how its magnetic field is oriented when it arrives. That is the visitor now approaching. If we could step far back and take in the Earth-facing side of the sun as a whole, the scene would not be a single isolated blemish on a quiet disk. It would look active, crowded, and unsettled. As this is being recorded, 9 separate active regions are numbered on the side turned toward Earth. The largest tangled regions remain the most complex among them, while other areas close behind are also being watched. The daily sunspot count has been running well above the monthly averages seen recently, which gives the week a broader context. This is not a quiet sun surprising us with one sudden outburst. It is a sun that has been energetic for days, and there is little sign that the activity has simply ended. One additional measurement from this week deserves to be kept in mind, because it becomes important when we think about satellites. At the altitudes where spacecraft operate, high-energy electrons surged. Forecasters watch a particular level, 1,000 units of electron flux. Passing that mark triggers an automatic alert, because those rapid electrons can begin creating serious difficulties for spacecraft. On the 6th of June, the flux did more than move past that warning line. It reached 1,284. That number may seem abstract in isolation, but it marks a kind of threshold in near-Earth space. Later, When we consider what a geomagnetic storm can do to the satellites woven into modern life, it will no longer feel like just another measurement. There was another particle warning during the week as well, though it points toward a different kind of vulnerability. Along with the elevated electrons, high-energy protons also increased after the flaring. Protons are heavier particles, and when the sun accelerates them to high energies, they become a radiation concern. This kind of hazard matters especially for astronauts outside the shielding of the lower atmosphere. And in the most severe cases, it can also matter for crews and passengers aboard aircraft on high-altitude polar routes, where the atmosphere above is thinner and magnetic protection is weaker. The enhancement this week remained modest, far below the point that would require protective action. It was more like a faint coating than a full storm. Still, even a small signal helps reveal the wider nature of solar danger. The sun does not only disturb wires, circuits, and magnetic fields. In an extreme solar proton storm, radiation levels in space and in the upper atmosphere can rise sharply. Airlines may reroute flights away from polar regions to reduce exposure for crews and passengers. Astronauts outside substantial shielding would face a real medical risk. This adds another layer to the story. Not just machines in orbit, not just power grids below, but human bodies as well. A star that looks calm from a distance can, under the wrong conditions, reach into systems we rarely think of as exposed. At this point, a reassuring idea may naturally come to mind. Is the sun not supposed to be calming down? There is truth in that question, and that truth actually makes the present situation more interesting. The sun follows in one-year cycle, moving from quieter conditions into stronger activity and then back again. We are now beyond the maximum of the current cycle, the one scientist's number 25, and it is entering what is known as the declining phase. It is tempting to imagine that a declining sun must be a safer Sunday. The record, however, is more subtle. By some measures, this cycle has behaved comparably to the historically strong cycles of recent decades, even though its raw sunspot count has been clearly lower, something like a quarter below the strongest of those earlier cycles. That contrast suggests that the energy of the cycle may be concentrated in ways a simple spot count does not fully describe. Activity can be packed into the rapid, high-frequency turbulence of the sun's outer atmosphere, still generating major flares and eruptions even while the headline numbers imply that conditions should be easing. In that sense, a sun still producing X flares and sending Earth-directed clouds during its declining phase is not following the simple story we might prefer. It raises a quieter but more important question. What if the measure that seems comforting is not the measure that matters most? The historical record removes even more of that easy comfort. Some of the most damaging geomagnetic storms known did not occur at the loudest peak of their solar cycles. They struck on the downward slope, in the declining phase, the same broad stage we occupy now. The great storm that brought down Quebec, which we will return to in detail, arrived during the declining phase of its cycle. The Carrington Event itself also hit while its cycle was fading. Scientists have examined why this can happen. Looking at the way the sun's large-scale magnetic structures reorganize as a cycle ages, those changes can open paths for fast streams of solar wind and help create long-lived geo-effective conditions, the kind capable of driving serious storms. The declining phase, then, should not be treated as the safe interval by default. In some respects, it may be one of the times that deserves the closest attention. Being past the peak is not, by itself, a reason to relax. It may instead mark the part of the cycle when vigilance becomes especially valuable. So, this is the week laid out in sequence. A tangled solar region, a triple flare crowned by an X, a confirmed direct hit on the 5th, a billion-ton cloud launched on the 6th, a sun dotted with active regions, a rise of fast electrons into the danger zone, and one-year cycle that is meant to be settling down yet continues to resist that simple expectation. Each element is the smaller version of a larger possibility, almost like a rehearsal. The pattern does not guarantee disaster, but it does show why space weather is watched so carefully. In the quiet language of measurements and alerts, something vast is unfolding between the Sun and Earth. The same solar regions, the same eruptive flares, the same billowing clouds of plasma, and the same underlying physics can become something entirely different when the scale is large enough and the aim is precise enough. What looks, from far away, like another burst from the Sun, can become the kind of event we are right to take seriously. Yet the most unsettling part is not simply the violence of the eruption, it is that even trained space weather specialists cannot state with certainty, well in advance, whether the next day will bring a mild disturbance or a severe geomagnetic blow. That uncertainty is not a weakness in the forecast. It is built into the nature of the hazard itself, and it is one of the reasons this subject deserves such careful attention. This is where the story becomes almost paradoxical. Forecasters may watch a coronal mass ejection leave the Sun, estimate how large it is, measure how quickly it is traveling, and follow its progress through interplanetary space. Even with all of that information, they may not know until roughly an hour before arrival whether the storm at Earth will be modest or extreme. That can sound, at first, like a failure of prediction. In reality, it reflects the physics of magnetic fields. The most important detail is hidden inside the cloud, and it cannot be fully sampled until the cloud is nearly upon us. When a coronal mass ejection reaches Earth, it is not like a stone striking glass. Our planet sits inside a protective magnetic envelope called the magnetosphere, produced by the motion of molten iron deep within Earth's core. This magnetic bubble normally turns aside much of the continual stream of solar particles flowing outward from the sunday. So when a CME arrives, the first concern is not only its speed, density, or size. The deciding question is the direction of its magnetic field. In space weather, that single orientation can make the difference between a storm that mostly glances away and one that couples powerfully into Earth's magnetic environment. The plasma cloud brings its own magnetic field with it, already embedded in the eruption as it leaves the sunday. That field has a direction, and for Earth, the crucial question is whether it points northward or southward. Forecasters refer to this as the BZ component. If the incoming field points north, in the same general direction as Earth's field at the front of the magnetosphere, the two fields are aligned in a way that tends to resist deeper interaction. The CME can then be pushed around the magnetic bubble, rather like water parting around the bow of a ship. Even a fast, dense, formidable CME may produce a surprisingly restrained storm if its magnetic field is northward at the key moment. In that case, the shield largely does its job. A southward field changes the situation. Then the incoming magnetic field is opposite to Earth's. Opposing fields can link together through a process called magnetic reconnection. Instead of simply pushing past one another, they connect and rearrange, creating a pathway for energy from the solar wind to enter the magnetosphere. In effect, the protective system becomes less like a sealed barrier and more like a door that has been opened. The same CME, with the same speed and mass. They can therefore produce a very different result depending on the orientation it carries when it arrives. This is the quiet but critical hinge in the entire forecast. The frustrating part is that this orientation cannot be measured with confidence from far away. A spacecraft sits about 1 million miles upstream of Earth at a special location known as the first Lagrange point, where the gravitational influences of Earth and the Sun allow a spacecraft to remain more or less stationed between our planet and the star. Instruments placed there sample the solar wind before it reaches Earth, giving us an essential early warning. It is a remarkably useful arrangement, almost like a tripwire stretched across space. but it comes with a hard limit imposed by distance and speed. For a cloud moving at more than 1,000,000 miles an hour, 1,000,000 miles of warning amounts to only about an hour. So the sequence can feel almost cruel. Scientists may track the CME for 2 days as it moves outward from the Sunday. Then, only in the final stretch, when the spacecraft at the first Lagrange point is swept by the approaching solar wind, does the magnetic orientation become clear. At that moment, forecasters can finally judge whether Earth's magnetic shield is likely to stay comparatively closed or whether reconnection may open the system to a much stronger storm. The most decisive information arrives last. That is why space weather prediction can be both advanced and deeply uncertain at the same time. It is worth pausing over magnetic reconnection, because that phrase carries much of the meaning here. Magnetic field lines usually behave as though they keep their own identities, bending and sliding rather than simply merging through one another. But when two magnetic fields pointing in opposite directions are forced together, as when a southward pointing cloud field meets Earth's northward pointing field at the front of the magnetosphere, the arrangement can break and reform. Field lines snap into new connections. In that reshuffling, plasma tied to those fields can be flung away at very high speed, while stored magnetic energy is released into the surrounding system. The idea is subtle, but its consequences can be dramatic. This same basic process is also involved in powering flares on the Sunday. In the case of a geomagnetic storm, however, it is unfolding on a smaller scale near our own planet. If the CME's magnetic field is northward, reconnection is inefficient and much of the cloud is diverted. If it is southward, reconnection can proceed far more strongly, and the magnetosphere behaves like a circuit suddenly energized. This image is not exact in every detail, but it helps convey the transition. The system is no longer merely resisting the solar wind, it is being loaded with energy. That energy does not remain only at the point where reconnection first occurs. It is carried around Earth and into the long magnetic tail that stretches away from the planet on the night side. There, energy can accumulate, rather like water building behind a dam. Eventually, the tail can also reconnect, sending a release of stored energy back toward Earth. This returning surge helps drive powerful electric currents high in the atmosphere and contributes to auroras that brighten and move rapidly during the most active stages of a storm. The magnetosphere becomes a kind of engine, taking in energy, storing it, and releasing it again. In a strong storm, that engine can run hard for hours, with each cycle pushing the magnetic field at the ground a little more forcefully. This is why severe storm forecasts sometimes seem to fade into almost nothing. The CME may arrive, but its magnetic field may be oriented in the less dangerous direction. The result can be a predicted G4 that behaves more like a G1, not because the cloud was imaginary, but because the coupling with Earth was weak. Depending on one's perspective, that outcome can feel like disappointment or relief. It also reminds us that the absence of a dramatic event does not mean the risk was misunderstood. It may mean the final magnetic alignment spared us the stronger version. There was a real example of this during the very week under discussion. The geomagnetic storm that arrived on the 5th of June, the confirmed direct hit, was expected by some early assessments to be stronger than it ultimately became. The cloud did arrive. The magnetic field strength rose to several times its normal value. The solar wind accelerated, and the density increased. In other words, many of the ingredients for a significant storm were present, but for portions of the event, the field orientation did not line up in the way that produces the worst effects. It pointed northward when the more dangerous outcome would have required a southward direction, and in that quiet detail, the difference between alarm and relative restraint may be found. What arrived, in the end, was not the severe geomagnetic storm that the early ingredients seemed to allow for, but a more restrained one. It climbed to G2, briefly brushed the edge of G3, and then faded. That is the uncertain coin toss of space weather made visible. and it happened in real time just 2 days ago. It is worth being direct about that, because the same thing could happen tomorrow. The incoming storm may fall short of expectations. The magnetic field could point north. The connection to Earth's field could remain weak, and the result might be a subdued display, with auroras staying farther poleward than many people hope, and little disruption beyond that. If that is how it plays out, it would not mean the forecasters misunderstood the physics. It would mean they identified the solar cloud correctly, but lost to a magnetic orientation no one could measure early enough. Space weather prediction is among the most difficult forecasting problems we face. Partly because the solar system itself gives us only a narrow view before the impact. There is a strange comfort in that uncertainty, but only at first. The same hidden orientation that can turn a threatening storm into a disappointment can also turn an underestimated one into something far more dangerous. A northward field can shield us. A strongly southward one can open the magnetic door and let the energy of the cloud pour into Earth's system with far less resistance. So the unpredictability is not simply a mercy, it is also a vulnerability. In a quiet voice, the sun reminds us that we are always making a wager, and the rules are not ours. This is where preparation meets its hardest boundary: time. Once the solar cloud passes the monitoring spacecraft upstream of Earth, there may be only about an hour before it reaches us. That hour is the usable warning. If procedures already exist, if grid operators have authority to move quickly, if training has made the response almost automatic, that short interval can matter. They may be able to reduce load on vulnerable transformers, shift the network into a more cautious configuration, and brace the system before the storm current begins to bite. Used well, an hour could separate a grid that survives under strain from one that fails under pressure. But an hour is also painfully brief. It is not the time to debate whether the danger is real, to invent a plan, or to decide who is allowed to act. The warning is small, and the consequences could be enormous, which means the serious work has to happen beforehand, during the calm years, when the threat still feels theoretical. That is the difficult politics of foresight. Spending effort, money, and attention on a storm that has not yet arrived. Physics gives us the hour. Whether we have built the discipline to use it is a human question. Before we move on, one piece of physics needs to be placed carefully, because it connects everything that follows. When Earth's magnetic shield opens and energy streams inward, immense electric currents are driven high above us in the atmosphere, especially over the polar regions. Those upper air currents shift, surge, and reorganize, and as they do, Earth's magnetic field down at ground level begins to change quickly. It pulses, swings, and jolts. That may sound like a technical footnote, but it is the central mechanism. Nearly 2 centuries ago, Michael Faraday showed that a changing magnetic field produces an electric field, and if that electric field finds a long conductor, a current begins to flow. During a strong geomagnetic storm, the magnetic environment over a vast region is changing rapidly, and across those same regions, humanity has stretched the longest conductors it has ever built. Power lines running for hundreds and thousands of miles, pipelines, railways, and undersea cables. Each one can act, in its own way, like a receiver for storm-driven current induced through the ground. At a level rated 7 tomorrow, that current would likely be more of a trickle than a torrent, something operators can manage without most people ever noticing. Yet the process is real, and once it begins, it points toward the larger danger. The essential question is simple and unsettling. What happens when the trickle becomes a flood? That is not just a theoretical concern. It has happened before, more than once. And each time, our good fortune was part of the story. To see what that flood means, picture not a household cord or a small wire, but a high-voltage transmission line, held aloft by steel lattice towers and stretched across open country. It may carry electricity from a distant power plant toward a city far away, running for hundreds of miles as one piece of the larger network. Across developed nations, tens of thousands of miles of these lines are stitched together, forming the arteries of modern civilization. In ordinary life, they are so dependable that they almost disappear from thought. During a strong geomagnetic storm, however, they can take on a second role, one their designers did not build them primarily to perform. They become collectors for the current that the storm has induced in the ground beneath and around them. And this storm-driven current is not the kind of electricity the grid is meant to handle. The electrical system is engineered around alternating current, a smooth, predictable rhythm that reverses direction 60 times a second. That rhythm is built into the design assumptions of the entire machine. A geomagnetic storm, by contrast, pushes something much slower into those long conductors. For practical purposes, it behaves like direct current, moving in one direction as a broad, heavy surge rather than the fast back-and-forth motion the grid expects. We call it a geomagnetically induced current, and for the most important equipment in the system, it is deeply dangerous. The vulnerable target is the transformer. It is helpful to linger on these machines because their importance is almost hidden by their silence. Most of us have passed hundreds of them without noticing. They have no glowing screens, no dramatic movement, no obvious sign that civilization depends on them. They sit behind fences or beside substations, humming steadily through season after season, performing a quiet translation without which the grid would be almost useless. Transformers take the very high voltages needed to move power efficiently over long distances and step them down, stage by stage, until electricity can safely reach factories, neighborhoods, and homes. Remove that translation, and the system becomes little more than an immense web of wires with no practical delivery at the end. That is why geomagnetically induced current matters so much. It is not merely an odd electrical effect in the ground. It is a pathway from a disturbance in near-Earth space to the hardware that keeps modern life illuminated. The storm does not need to strike a transformer directly. It only needs to change the magnetic field, induce the current, and let our own long conductors carry that current into places where the grid is least comfortable receiving it. In that quiet connection, the space weather story becomes an infrastructure story, and the sky reaches down into the machinery we usually take for granted. Among the countless components that keep modern power moving, only a small fraction are both enormous and absolutely pivotal. These are the extra high voltage transformers stationed at the major hubs of the grid. And if even a few of them were lost in the wrong locations, the wider network might not be able to route around the damage. In a quiet, almost invisible way, civilization rests on these humming grey machines. Equipment most people never notice. Equipment that can require close to a year to replace, and equipment that a severe solar storm could damage from within. That is the hidden support in the system, the part no one tends to think about until it stops working. It is a little like looking at the night sky and realizing that the calm surface hides forces moving on a scale far beyond daily life. You have almost certainly passed transformers before, perhaps without giving them a second glance. Large grey boxes inside substations, set back behind chain-link fences, vibrating softly as they do their work. Their task is simple to describe and essential to perform. They raise voltage so electricity can travel efficiently across long distances, then lower it again so it can be delivered into neighborhoods. Without them, the grid does not truly operate as a grid. The largest members of this family, the extra high voltage transformers located at the great nodes of the system, are extraordinary industrial machines. They may weigh hundreds of tons, hold thousands of gallons of cooling oil, and are designed with great precision for alternating current. What they are not designed to accept is a slow, one-directional, geomagnetically induced current arriving alongside the ordinary power. When that unwanted current enters, it affects the transformer's core in a way engineers describe with one restrained but unsettling word: saturation. In that single term, the danger becomes physical. To understand saturation, imagine the transformer as a device that transfers energy from one coil of wire to another through a magnetic core. Under normal conditions, that core's magnetism swings back and forth in rhythm with the alternating current, like a controlled pulse moving through iron. The entire design depends on that balanced oscillation, but the slow current induced by a storm adds a steady magnetic offset, pushing the core away from its center point. For part of the cycle, the core is forced into a condition where it can no longer take in additional magnetism. That is saturation. And once it happens, the transformer can begin failing in several ways at the same time. It can overheat, sometimes severely, as internal hotspots develop, insulation cooks, and windings are charred. It may also pull huge amounts of reactive power, which can weaken voltage stability across the network. At the same time, the normally smooth electrical waveform can be warped into a jagged pattern rich in harmonics, and those distortions may spread outward, disturbing protective devices elsewhere on the grid. The concern is not just one machine behaving badly. It is the possibility that its distress becomes contagious across the system. The process is worth lingering over, because saturation is the physical center of this entire failure scenario. Deep inside the transformer sits a core made from specially engineered iron. Alternating current creates a magnetic field there, and in ordinary operation, that field reverses cleanly. North, then south, then north again, 60 times a second. This repeated swing is what allows energy to pass from one set of windings to the other. Yet iron has a limit. It can hold only so much magnetism. And the transformer is built so that, during normal service, each magnetic swing remains safely below that ceiling. A storm-driven one-directional current changes the balance. It is as if pressure were applied to one side of the oscillation, shifting the whole motion off-center. During one half of each cycle, the core can be pushed past its limit into saturation, where it cannot absorb more magnetism. The energy that should have moved smoothly through the core then leaks outward as stray magnetic flux into the transformer's surrounding metal structure. This is where the invisible becomes damaging. That stray flux releases energy as heat in places that were never meant to become hot. Those vulnerable places include structural steel, clamps, and the tank walls. Hotspots can form quietly inside the machine. The cooling oil may begin to degrade. The insulation, often essentially specially treated paper, can start to char. A transformer is, in one sense, a carefully balanced instrument built to perform a single task with remarkable reliability. A solar storm disrupts that balance by forcing it to operate outside its intended design. In the worst case, the transformer does not merely trip offline or behave erratically for a while. It is destroyed. Heat accumulates faster than the cooling system can remove it. Insulation fails, and the machine suffers permanent physical damage. This distinction matters deeply. A tripped device can be restored. A ruined transformer is not simply switched back on after the storm passes. Sometimes that destruction is unmistakable. A transformer may catch fire or rupture its tank. More often, the damage can be quieter and more deceptive. Internal injury may not reveal itself at once, yet it can leave the machine fatally weakened. It might fail days or weeks later, or be judged too compromised ever again to carry the grid's full load safely. That delayed uncertainty is part of what makes the threat so difficult to manage. The system may appear to have survived, while essential hardware has already been wounded. For a network that depends on trust in each component, even hidden damage raises a serious question. How much unseen harm can the grid absorb before recovery becomes far harder? There is, however, a defense, and it is important because it marks the boundary between enduring a major storm and being overtaken by it. Engineers can install equipment that prevents geomagnetically induced current from reaching transformers in the first place. Capacitors and resistors can be placed in the connection to the ground, blocking the slow direct current while still allowing the normal alternating current to pass. In broad terms, the technology needed to harden the grid is already known and largely available. It is not a mystery waiting for discovery. The more difficult obstacle is practical and institutional. Strengthening a continent-spanning grid is costly, slow, and complicated. It asks utilities, regulators, and governments to spend heavily on protection against a danger that has not occurred within their own lifetimes. Hazards that are invisible, rare, and yet potentially severe are exactly the kind human systems often struggle to rank ahead of immediate needs. So hardening moves forward unevenly, in patches, while the grid continues to expand and become more interconnected. We know the protective path. We have, for the most part, not fully taken it. This is the central point of the threat, and it deserves to be separated from the simpler idea of a blackout. Losing a transformer is far worse than losing power for a time. The difference is the difference between inconvenience and catastrophe. When the grid trips offline to protect itself, recovery is usually possible. Operators can reroute electricity, bring power plants back online, and restore service, sometimes within hours. In that situation, the trip is not the failure of the system. It is the system trying to save itself. A destroyed extra high voltage transformer belongs to another category. It creates a hardware problem, not just an operational one. And the reason is stark. These machines are not waiting in warehouses, ready to be plugged into place. The largest transformers are not mass-produced items. Each one is, to a significant extent, custom-built for the exact location in the grid where it is meant to serve, engineered for specific voltage and capacity requirements. Constructing one is a major industrial project, and from order to delivery, it can take many months, sometimes more than a year. In the calm language of infrastructure, that delay may be the most sobering fact of all. Much of the global ability to build these giant transformers is concentrated in a small number of highly specialized plants, often separated by oceans from the grids that may one day need them most. Their size alone turns transportation into an engineering project. A single unit can demand special rail cars, heavy-haul trucks, and a route planned with unusual care. Just as important, no nation maintains an immense stockpile of replacements waiting in reserve. There are limited backup supplies and mutual aid agreements, but nothing on the scale required if a solar storm were to damage not a few transformers, but dozens or even hundreds across a continent at the same time. This is where the danger becomes less dramatic and more quietly difficult. In a familiar disaster, such as a hurricane or an earthquake, the destruction is usually bounded by geography. Crews can arrive from neighboring states. Equipment can be moved in from places that were spared, and the wider system bends toward the injured region. A geomagnetic superstorm is different because it does not politely choose one region and leave the rest untouched. Its induced currents can enter long transmission lines over a whole continent at once. If the event were powerful enough, those currents could saturate and ruin major transformers in many locations simultaneously. Then there would be no untouched district with enough spare equipment to offer. No hidden warehouse filled with ready replacements, and no quick manufacturing path that avoids many months of waiting. The outage, in that scenario, would not behave like a normal blackout that crews simply repair and close out. It could become a long interval, endured in darkness, perhaps through a season or beyond. That possibility matters because it changes the nature of the risk. The problem is not only whether power fails, but whether the system can be restored on ordinary human timescales. Beneath that larger concern lies a quieter detail, one that helps determine which places suffer most. The current driven through the ground depends not solely on the storm above, but also on the character of the earth below. In regions where subsurface rock conducts electricity reasonably well, some of the induced current can travel through the ground itself, leaving less to be pushed upward into the power network. But where the bedrock is old, crystalline, hard, and a poor conductor, as in broad areas of North America and Scandinavia. The ground offers a less useful route. The current then seeks an easier pathway, and a long grounded transmission line overhead becomes a tempting alternative. This is one reason the Great Northern Grids, built across ancient shield rock and stretched over long distances to move electricity from remote generation, rank among the most exposed systems on the planet. The geology under a house, the stone most people never consider, may help decide how severely a solar storm affects the lights above it. It is a modest-sounding variable, yet in a hazard filled with uncertainties, it can shape the map of consequences. The worst-case picture of a great storm would therefore not be smooth or evenly spread. Some places rest on a kind of natural buffering, while others sit on terrain that makes the grid more vulnerable. And the lines serving tens of millions may cross directly through the harshest combinations. Nor is the electrical grid the only structure that can act like an antenna when the sky becomes magnetically disturbed. Any long conductor can be drawn into the event. Continental pipelines carrying natural gas and oil can develop induced currents that speed corrosion and mislead monitoring systems. Railway signaling can be affected. Undersea communication cables, the physical backbone of the global internet, can also carry induced currents during the most intense storms. In such a moment, Earth's industrial web begins to look less like separate infrastructure and more like one connected metallic nervous system, energized from above by a shifting magnetic field. Every wire humanity has stretched across land or sea becomes, in some measure, part of the same immense circuit. Tomorrow, that mechanism will awaken only gently. Induced currents will move. Transformers may experience a small rise in heat and reactive demand, and operators will handle it because a storm rated 7 is merely a weak flow through equipment strengthened by lessons from earlier events. You will not lose electricity tomorrow because of the sun. Still, the process that leaves your light steady tomorrow is the same physical process that, on a far larger scale, could extinguish them. The difference is not the kind of mechanism, but the volume of the flood. To grasp how large that flood can become, we must return to a September night in 1859, when the sun produced an event unmatched in the era of human record-keeping. It did not end the world for one simple reason. The world of that time had very little technology for it to break. This brings us to part 5, the 1859 benchmark. On the morning of the 1st of September, 1859, the English astronomer Richard Carrington was engaged in a routine he followed on many clear mornings. At his telescope, he projected the sun's image onto a screen and carefully drew the sunspots drifting across its surface. For several days, he had been watching an especially large and complicated cluster of spots. Then, while he observed and sketched, something appeared that no one had recorded before. Within the dark sunspot group, 2 points of brilliant white light suddenly flared into view, so bright that Carrington first suspected sunlight had somehow entered his apparatus through an unintended path. It had not. He was witnessing, with human eyes, the first recorded solar flare, an eruption powerful enough to show itself in white light against the already dazzling face of the sun. Carrington wrote down the time, though he could not truly know what he had seen. No one really could. The notion that the sun might reach across space and physically disturb Earth was, at that stage, little more than a developing idea. Yet, Earth was about to be struck more strongly than it has been in all the centuries since. What makes the event carrying Carrington's name so extraordinary is not only the flare itself, but the accompanying cloud and the speed with which it arrived. A typical coronal mass ejection needs 2 to 4 days to travel from the sun to Earth. The one released that morning in 1859 made the journey in roughly 17½ hours. That number is worth pausing over. To cross such a distance so quickly, the cloud must have been moving with an intensity almost beyond ordinary description, driving through the solar wind before it, carving a path and reaching Earth with much of its energy still intact. It remains the fastest major Earth-directed cloud in the entire record. When it struck, Earth's magnetic field lurched so violently that the simple magnetometers of the time, scattered in different places around the world, swung completely beyond their scales. Then the wires began to behave in ways that seemed impossible. In 1859, the telegraph was the marvel of modern communication, the first technology that let information outrun a horse. Across continents, copper wire formed a new human network. On the night the Carrington storm arrived, that network seemed almost taken over by the sky itself. In the telegraph offices, the first signs were not subtle. Operators described sparks snapping from instruments, with electrical arcs reaching toward their hands and faces. Paper used for messages sometimes ignited as current surged along the lines. In a few places, the disturbance became so strong that batteries, normally the heart of the system, were taken out of the circuit altogether, and the messages still went through. For a brief interval, the wires were no longer being driven by the equipment in the room. They were being driven by the storm overhead. It is one of the most arresting details in the records of the Carrington event. Two operators, linked between two cities, found their apparatus so overwhelmed that they removed the usual power source, apparently expecting the night's work to be finished. Instead, the line continued to carry their signals on the current produced by the aurora itself. The Earth's magnetic upheaval had become, in effect, a telegraph battery. That image is almost serene in its strangeness, and yet deeply unsettling. It shows, with unusual clarity, the central lesson of the event. A major solar storm can drive real electrical current into the long conductors human beings stretch across the landscape, current strong enough to be useful for a moment and destructive the next. Above those sparking instruments, the sky was performing on a scale few people had ever imagined. Auroras are usually associated with polar regions, glowing near the high latitudes around the magnetic poles. During the nights of the Carrington storm, however, they moved far beyond their expected territory. Reports placed them in the Caribbean and close to the equator. Across the lower United States, people woke in darkness and thought sunrise had arrived ahead of time. Red and green light filled the sky so intensely that newspapers could be read outdoors. In the Rocky Mountains, miners rose and began preparing breakfast. Certain morning had come, even though it was 0 inches the morning. Birds, misled by the artificial dawn, began to sing. The accounts are spectacular, but the spectacle is only part of what matters. Beneath it is a quieter human story. People confronted with a sky they could see plainly, but could not interpret. They had no language for coronal mass ejections. They did not understand geomagnetically induced currents. They did not know that the sun had expelled material toward the earth. What they knew was more immediate. The night had turned the colors of flame and blood, telegraph machines were throwing sparks, and something immense had arrived from above without warning. Some observers were amazed, others afraid, and some, living in an era more open to such readings, regarded it as an omen. The mechanism remained beyond them, because the necessary science had not yet been built. Our situation is almost the mirror image of theirs. Today, the broad physical cause is understood. We know the sun can launch powerful eruptions. We know how they can disturb Earth's magnetic environment, and we know the kinds of systems that may be placed at risk. In that sense, we possess the framework that people in 1859 lacked. Yet this knowledge has not made the danger disappear. There is something almost darkly ironic in that. Understanding a hazard and preparing for it are not the same achievement. One belongs to explanation, the other belongs to action. And the troubling possibility is that modern civilization has become very good at describing the threat, while remaining far less complete in hardening itself against it. This is why the Carrington event still matters. It is not merely a historical curiosity, not just a night when the sky glowed in impossible colors. It is a test case. a natural demonstration of what happens when the sun's activity couples itself to human technology. Consider the difference between then and now. In 1859, what was there for the storm to attack? Mostly the telegraph, a limited web of wire, batteries, and instruments, stretching for a few thousand miles by the standards of the time. There was no global electrical grid, no satellites circled overhead. There were no computers, no electronic banking systems, no internet, no refrigerated supply chains, no electrically driven pumps moving water through cities, and no modern network of communications and medicine depending on continuous power. The most advanced electrical technology available to a violent solar storm was the telegraph. It burned paper, shocked operators, and then history largely moved on. Humanity did not suffer a collapse because humanity had not yet built very much that such a storm could collapse. The vulnerability had been revealed, but the target was still small. We are not living in 1859. In many ways, we are its opposite. Over the century and a half that followed, human beings built a world around precisely the kinds of systems the storm exposed as vulnerable. The long wires that once carried a few messages now form the nervous structure of civilization. Into them we have tied food, water, money, heat, medicine, communication, and the daily machinery of ordinary life. The old lesson was simple. A geomagnetic disturbance can push current into extended conductors. Instead of moving away from that weakness, we expanded it across the planet. This does not mean the sun has become more dangerous than it was during the Carrington event. The more unsettling conclusion is that we have become more exposed. We constructed the larger target ourselves. If a storm of comparable scale could once pass through a world of horses and telegraph offices with limited lasting damage, the same kind of event now raises the possibility of costs measured in trillions and recovery times that could stretch for years. The benchmark has not changed in the sky. What has changed is the civilization beneath it. There is also physical evidence, written not in human testimony but in the planet's own archives, that suggests how extreme such storms can be. When energetic particles from a powerful solar event strike Earth's upper atmosphere, they can help produce compounds including nitrates, which eventually settle and become trapped in polar ice. Layer by layer, year after year, that ice preserves a chemical record. Scientists can drill ice cores and examine those layers much as tree rings are read, searching for traces left by past solar activity. Alongside that, radioactive signatures produced by cosmic bombardment can be studied in tree rings, giving researchers another way to look backward across long spans of time. These records do not turn the past into a simple story, but they offer a sobering suggestion. Events on the scale of Carrington, and possibly larger, appear in historical and prehistoric evidence. That matters because 1,859 may not represent the upper limit of what the sun can do. It may simply be the largest example that human beings happen to witness with instruments, however limited those instruments were. The quiet implication is difficult to ignore. Carrington is not necessarily the ceiling. It may only be the best-known marker. From there, the question becomes both simple and uncomfortable. How often does the sun produce something like the Carrington event? The honest answer is that precision is difficult, because the detailed instrumental record is short. Still, the estimates often gather around a rough frequency of once or twice per century. Once or twice per century is not a distant geological rhythm. The last confirmed event of that scale occurred more than 160 years ago. However one chooses to think about the arithmetic, it does not place us safely outside the interval of concern. It suggests that we may already be living within the period when another such storm is plausible. And this is the final contrast that gives the story its weight. The storm that once set telegraph paper alight in a world powered largely by muscle, flame, and steam would arrive today over a society that depends, hour by hour, on electrical systems and networks. That is the measure by which Carrington remains so important. It is not only a memory of what the sun did once, it is a quiet standard against which the resilience of the modern world must be judged. Let us come, quietly, to the clearest modern glimpse of what this kind of space weather can do on Earth. The night an entire province lost its power in roughly 90 seconds. Part 6 brings us to 1989 and to Quebec in the dark. A little after 2:30 inches the morning, on the 13th of March 1989, more than 6 million people across the Canadian province of Quebec were asleep in the cold of a Canadian March. Many homes depended on electricity for heat, and far to the north, the great hydroelectric dams were still sending power southward through long transmission corridors toward the cities. Everything appeared to be functioning in the ordinary way, until the system unraveled almost all at once. For hours, a geomagnetic storm had been intensifying, born from a large solar eruption that had left the sun days before. As the storm interacted with Earth, geomagnetically induced currents began entering the long power lines descending from the northern dams. Those lines were vulnerable not only because of their length, but because they crossed ancient rock that conducts electricity poorly. In practical terms, that poor conductivity can encourage more of the induced current to move up into the electrical grid itself. It is a quiet detail, but an important one. The ground beneath a power network can help decide how strongly a storm in space is felt by machines on Earth. Inside the grid, the unwanted currents drove equipment towards saturation. Voltage started to fluctuate. Protective systems, built to defend the network from dangerous conditions, began detecting something profoundly abnormal. One component disconnected. Its burden was immediately pushed onto other parts of the grid, which were already under stress, and those parts then exceeded their limits and disconnected as well. In about a minute and a half, the failure became a chain reaction. The Hydro-Quebec grid, carrying around 21,000 megawatt, went down. That number is not abstract. 21,000 megawatt is the scale of a major power system, enough to supply a province. Then, in the cold darkness, it vanished. More than 6 million people lost electricity. Heating systems stopped. The Montreal subway halted. The airport went black. For about 9 hours, crews worked to understand the failure and restore the grid carefully, section by section. What lingers is not only the blackout, but the speed. This was not a slow decline that operators could watch, diagnose, and steadily resist. It was a cascade, and a cascade in an electrical grid can move almost as fast as the electricity itself. The trouble began when geomagnetically induced currents made parts of the system behave unpredictably, and a critical piece of voltage regulating equipment tripped offline to protect itself. Once that happened, the load it had been carrying had to go somewhere. It shifted onto the remaining network, which was already strained. Then other equipment crossed its limits, tripped in turn, and forced still more load onto fewer surviving components. The pattern was simple and ruthless, like dominoes spread across a province rather than lined up on a table. Before a human operator could fully absorb that the first major piece had failed, the wider system was already collapsing. There was no meaningful time to intervene. No person in the control room could react quickly enough to change the outcome. That is the unsettling lesson. A geomagnetic storm can turn the built-in protections of a power grid into part of the sequence that brings it down. In 1989, it did exactly that to a grid that, by the larger standards we are considering, was only moderately challenged. A 9-hour outage is survivable. People waited, wrapped themselves against the cold, and eventually the lights returned. In the language of disasters, the Quebec blackout was a harsh night, not the end of civilization. Yet that is precisely why it matters so much, because the event carries two facts that sit uneasily beside one another. The first is the mechanism. Quebec was not struck by some random malfunction, nor by a single unlucky piece of equipment failing in isolation. The event followed the expected physical pathway. Geomagnetically induced currents entered the grid, pushed transformers towards saturation, destabilized voltage, triggered protective shutdowns, and helped collapse a major electrical system. A subtle current became, for one province, something like a flood, and the effects were not confined to Quebec. The same storm extended into the northeastern United States. At a power station in New Jersey, a large transformer was driven so hard by those induced currents that it was not merely switched off, it was permanently damaged. A multi-million-dollar machine was effectively cooked from within by a storm that began on the sun. This is why the New Jersey case deserves a pause. It stands as one of the plainest reminders that transformer destruction is not just a theoretical scenario drawn on paper. The machine was a large generator step-up transformer at a nuclear plant, one of those custom-built pieces of equipment that can take the better part of a year to replace. During the storm, geomagnetically induced currents pushed it into the same saturation and overheating process we have been tracing. The internal damage was severe enough that the transformer was finished. Across 93 million miles, solar activity reached into a specific, identifiable piece of American infrastructure and ruined it. That did happen. It is part of the record, and it happened during a storm that was still far from the most extreme the sun can produce. So the question raised by 1989 is not whether transformers can be destroyed by such currents. That question was answered decades ago by one dead machine in New Jersey. The harder question is how many might fail, where they might fail, and whether replacement capacity could keep up if the number became too large. The second fact is what changes this from an account of history into a warning. By the standard of the sun's true potential, the March 1989 storm was not among the greatest. It was strong, certainly, and serious enough to expose deep vulnerabilities. But it was nowhere near the scale of 1859. It may have been perhaps a third, maybe less, of the intensity of a true Carrington-class event. Even so, that merely strong storm, only a fraction of the worst case, brought down an entire province's power grid in 90 seconds and destroyed a transformer hundreds of miles away. And the lesson extends beyond those two places, across the northeastern United States, and into grids in other regions. Operators spent that night trying to prevent their own systems from following Quebec into darkness. They watched voltage swing and equipment strain, with some systems coming closer to collapse than the public ever understood. In a calm retelling, the night can sound distant and contained, but it may be better understood as a small window into a much larger question. If that was what a lesser storm could do, what would a greater one ask of the same fragile architecture? Far south of Canada, electrical systems also felt the pressure building in the wires, while the auroras traveled with the storm in the way they often do when the sun disturbs Earth's magnetic field on a grand scale. That night, the northern lights appeared far beyond their normal territory, turning up in regions where they are rarely seen, reaching down toward latitudes associated with the Caribbean. In that sense, the event carried a faint reminder of 1859, not equal to it, but close enough to be unsettling. This was never simply a Canadian accident, or a single unfortunate grid collapsing in isolation. It was a continent-wide examination of electrical resilience, and Quebec became the first place where the strain overwhelmed the machinery most dramatically. Other systems endured, but not by the comfortable margin anyone would have preferred. And the storm delivering that test, worth emphasizing because the scale matters, was still far below the most severe event the sun is capable of producing. Pause for a moment with that comparison. If a solar storm much smaller than the worst case can bring down a regional grid in a minute and a half and damage a transformer in another country, then the natural question is unavoidable. What happens when the event is truly on the Carrington scale? The answer is not confined to a single province. It spreads across a continent. Geomagnetically induced currents would not enter only one set of northern transmission corridors. They could push into long power lines across an entire landmass at the same time. A failure would not merely trip one network. It could move through interconnected grids that cover whole nations, because those systems are deliberately linked so electricity can travel wherever demand requires it. Under ordinary conditions, that design is a strength. Under an extreme solar storm, it may become a weakness. If one region fails violently enough, the same connections meant to support it can help pull neighboring regions into the collapse. The damaged transformers would not necessarily be limited to one unit in New Jersey. They could number in the dozens, perhaps hundreds, spread widely across the map. Each would be a custom-built machine, difficult to replace quickly, often requiring the better part of a year, with no vast warehouse of spares waiting in reserve. Here lies one of the quiet ironies of modern infrastructure. We tied grids together intentionally, linking region to region and nation to nation, because, for common failures, that makes the system more dependable. When a power plant shuts down, surrounding areas can compensate. Electricity can flow in from elsewhere, the shortage is covered, and the lights remain on. Interconnection is an elegant shield against everyday breakdowns. But it is poorly suited to a threat that arrives everywhere at once. The wires that allow a healthy system to rescue a weakened one can also allow a collapsing system to infect a stable one. During a major geomagnetic storm, there may be no untouched region available to help, because induced currents are entering long conductors across the landmass simultaneously. What protects us from small, local disruptions can become the route by which a much larger failure spreads. In trying to solve the frequent disaster, we may have increased our exposure to the rare one. That does not mean the design was foolish. It means the risk belongs to a different category. Quebec's blackout in 1989 lasted 9 hours because the grid had been knocked down, not physically ruined. The equipment needed to restore service still existed, and it still functioned. Now imagine the harsher version, where the machines required to rebuild the grid are precisely the machines the storm has destroyed. That outage is not measured in 9 hours. It becomes a problem of months, and in that scenario, darkness is only the first layer of the crisis. Nearly every modern necessity sits downstream of electricity, and that dependence is easy to forget while the current is flowing. The water from a household tap is moved by electric pumps. Gasoline at a station is lifted from underground tanks by electric pumps as well. So in a prolonged blackout, cars and generators can sit beside fuel they cannot access. Food in stores and medicine in pharmacies depend on refrigeration powered by the grid. Money in a bank becomes numbers in machines that require electricity and networks to have practical meaning. Hospitals have backup generators, but those generators rely on fuel, and fuel is finite. A modern city is, in effect, an intricate machine designed to keep millions of people alive within a compact space. That machine runs on electricity. A severe geomagnetic storm is one of the few natural events capable of switching it off across an entire continent at once, and then damaging the components needed to restore it. Quebec, in 1989, was a survivable rehearsal. 9 difficult hours, followed by the return of power. It was the G2 of grid collapses, a warning on a smaller stage. We should be grateful for that warning, because it gave engineers real lessons, and the grid is more hardened today because of it. Still, a rehearsal is not the performance itself. The closest the modern world has come to that full performance, a Carrington scale event aimed into the satellite age, did not happen in some remote century. It happened within living memory, and Earth missed it by about 1 week. This brings us to the storm of 2012. The event that should perhaps have settled the question of whether such a thing can truly occur, because in a very real sense, it already did. Part 7, the one we missed by a week. On the 23rd of July, 2012, the Sun released one of the most powerful coronal mass ejections ever recorded by human instruments. It burst away from the solar surface and raced into space at a speed that, by some measures, rivaled or surpassed the 1,859 event. This was a true Carrington-class cloud, the kind of eruption researchers had long wondered whether they would ever be able to observe directly. And they did observe it with remarkable detail, because the cloud passed over one of the spacecraft positioned in the solar system to monitor exactly this kind of solar activity. Then it continued outward into empty space. Earth carried on as usual, and almost no one beyond the relatively small world of space weather scientists realized what had occurred. The reason the modern era survived one of its most powerful solar storms is almost blunt in its simplicity. It missed us. The solar region that produced the eruption was not facing Earth at the moment it fired, because the Sun, as seen from Earth, rotates roughly once every 27 days. Any given area on its surface spends only part of that time pointed in our direction. The July 2012 eruption came from a region that had been aimed directly at Earth about a week earlier. 1 week. Had the same eruption occurred 7 days sooner, while that active region was squarely facing us, the cloud would not have vanished harmlessly into open space. It would have struck Earth head-on, carrying its full violence into the world we had built beneath it. We have an unusually clear picture of what might have unfolded, because the spacecraft caught in the blast did not merely notice the cloud, it recorded it in detail. When scientists later modeled the same eruption as though it had intersected Earth, the result was deeply unsettling. By the standard index used to judge how forcefully a solar storm compresses and disturbs Earth's magnetic field, the July 2012 event would have approached the scale of the Carrington Event itself. And it would have been about twice as severe as the storm that collapsed Quebec's power system in 1989. In other words, this was not the kind of disturbance that leaves one region dark for 9 hours and then fades into history. A direct encounter with that cloud could have meant the kind of continent-spanning, transformer-destroying disaster measured not in hours, but in months. The quiet detail that spared us was not technology, or preparation, or warning. It was timing. Roughly 1 week in the Sun's rotation. That is a fragile kind of safety, and it gives the story its uneasy weight. Yet the near miss also left behind something valuable. Because the cloud passed straight over a spacecraft in the inner solar system, instruments designed to examine the Sun were able to take a full internal measurement of a genuine Carrington-class eruption, something they had never possessed before in this way. They captured its speed, its density, the strength of its magnetic field, the field's orientation, and the other properties needed to understand the threat without relying on speculation. Strangely, one of the most dangerous solar storms ever observed became one of the best documented. That matters because the conclusion does not rest on guesswork about what the cloud might have been. The data were there, and they indicated that if the eruption had arrived 7 days earlier, Earth would have met it at full strength. With a southward-leaning magnetic field, the combination most capable of coupling violently with our planet's magnetosphere. It was, in plain terms, the worst possible alignment. The metaphor almost writes itself. A loaded weapon discharged, its safety off, missing only because the barrel happened to be aimed a few degrees aside when the shot was fired. One scientist who studied the event later described the situation as passing through the crosshairs without being struck. While most people never realized we had been in danger at all, we escaped not by design, but by orbital luck, by being in the wrong place at precisely the right moment. There was no felt shock, no global alarm, not even the faint sensation of a cosmic wind slipping past. That closeness is what makes the event so sobering. It was not some distant 19th century warning pulled from the age of telegraphs. It happened in 2012. Within living memory for many people watching, and it suggests, with unusual directness, that the great solar storm is not simply a theoretical future possibility, A storm of that class has already happened in our era. It simply and mercifully missed Earth. It is worth pausing on that shift in perspective, because it changes the emotional character of the entire risk. Many large-scale dangers are discussed through probabilities, projections, and models of events that have not yet taken place, which makes them easy to place at a safe mental distance, as if they belong to another generation or another world. But a Carrington-scale solar storm no longer sits comfortably in that category. We do not have to wonder whether the sun is capable of producing one now, in the age of satellites and electrical grids, because it did so in 2012, and the instruments measured it. The only reason we are not describing that year as the beginning of a long recovery is geometry. The active region on the sun was not pointed at us on the day it erupted. Remove the comforting accident of the miss, and the picture becomes stark. In a modern civilization built around electricity, communications, and orbital infrastructure, the sun has already sent a world-altering solar storm across Earth's orbital path. The shot was fired. We saw the flash and measured the projectile. We simply were not standing in its path during that particular week. And the sun does not wait for human readiness before producing its next eruption. The next alignment may not be as forgiving. That near miss also lets us move from fear to estimation, because the question of cost has been studied by serious institutions. A major report by the National Academy of Sciences, which advises the United States government on these kinds of technical and scientific risks, examined what a Carrington-scale storm could mean for a society as electrified as ours. Their estimate for the economic impact in the first year alone fell between 1 and 2 trillion. Not billion, trillion. For the areas hit hardest, the projected recovery period was not a matter of weeks, and not even merely a few months. It was placed in the range of 4 to 10 years. That figure deserves to settle in the mind, because it may be the least intuitive part of the entire scenario. When we picture catastrophe, we tend to imagine a familiar rhythm. The disaster arrives, damage is assessed, repair crews move in, and life is gradually rebuilt. A hurricane passes, roads are cleared, buildings are repaired, power returns. Our instinct tells us that even a terrible event has an aftermath in which organized repair begins almost immediately. But a geomagnetic superstorm challenges that instinct because of the transformer bottleneck described earlier. The pace of recovery is not slow merely because there is a great deal to fix. It is slow because the very machines needed to restore the system are among the machines most likely to be damaged or destroyed, and they cannot be replaced quickly. Extra high voltage transformers can take the better part of a year each to build. There is no vast reserve waiting in warehouses, and only a limited number of factories can produce them. In an ordinary year, that narrow industrial base may be enough for routine replacement. In a planetary scale emergency, it becomes the limiting factor. The phrase 4 to 10 years does not mean the time required to sweep debris from streets or reconnect a few local circuits. It points to the time required to manufacture a path back toward a functioning grid. While large regions endure conditions modern societies have not collectively known since before electricity. A natural objection arises here, and it is understandable. Surely, in a crisis of that magnitude, industry would accelerate. Surely governments would mobilize production as they do in wartime. But the obstacle is not only urgency, it is physics, engineering, materials, and testing. An extra high voltage transformer is not a car on an assembly line, where the answer is simply to run the line faster. It demands specialized facilities, large quantities of particular high-grade electrical steel, copper, precision manufacturing, and a verification process that cannot safely be hurried. A transformer that fails after installation can become worse than a missing transformer because it may damage the fragile system it is meant to help restore. The number of factories worldwide able to build the largest units is small, and under normal conditions, they supply ordinary demand with limited excess capacity. Now imagine the developed world, all at once, placing emergency orders for the same rare machines. That is where the scale of the danger becomes quiet, mechanical, and deeply real. At the very moment when a shattered grid would need replacement parts, every damaged region would be reaching for the same limited supply of electrical steel, the same specialist factories, and the same narrow manufacturing capacity. Even the movement of those parts would be slowed, because global shipping depends on many of the same electrical systems a severe storm could disable. This is where the problem becomes colder and more mechanical. The line does not shorten in a season. It may take years, and the places farthest back are left waiting longest. No budget, however large, can force precision winding or transformer steel production to outrun the physical and industrial limits that govern them. That is why the recovery is spoken of in the language of 4 to 10 years, not 4 to 10 weeks. The obstacle is not simply reluctance or bureaucracy. It is a bottleneck created by missing preparation. The spares, the reserve capacity, the emergency manufacturing depth, those would have had to exist before the need arrived. And this is the quiet, unsettling lesson. A technological society can be damaged not only by what strikes it, but by what it failed to stock, plan, and harden in advance. Now, imagine what 4 to 10 years without dependable electricity would actually feel like across a large region. This would not resemble an extended camping trip or a temporary inconvenience endured with patience and batteries. It would mean the failure of the interlocking systems that make it possible for tens of millions of people to live densely in cities. Water networks would struggle because pumps require power. Sanitation systems would falter. Food distribution, tied to refrigeration and electric logistics, would begin to grind down. Medicines that need cold storage would become harder to preserve. Hospitals would burn through generator fuel, and even that supply would eventually face its own problem, because the pumps and networks that move fuel also rely on electricity. The dependencies that were exposed during Quebec's 9 hours would not be compressed into a single night. They would be stretched across years. The likely human cost is dark enough that there is no need to dwell on it in detail. The arithmetic is there. The modern world functions like an immense life support machine for crowded civilization, and the grid is one of its central organs. A geomagnetic storm does not merely switch that organ off. In the worst case, it damages the very equipment needed to bring it back. That distinction matters because it turns an outage into a recovery crisis. It is important to slow down here, because this subject can easily slide into catastrophe for catastrophe's sake. That is not the purpose. Laying out the severe case so carefully is not meant to leave us helpless. It is meant to show that this particular natural threat is unusual. In principle, we can see it coming, and in practice, we can prepare for it. We cannot prevent an earthquake from releasing its stored energy. We cannot persuade a hurricane not to form. But a geomagnetic superstorm is not mysterious in the same way. We understand the mechanism, how the currents are induced, why long conductors become vulnerable, which machines are placed at risk, and how damage can propagate through the grid. We know the kinds of devices that could block those currents. We know spare transformers could be built and stored. We know operating rules could be written so grid operators can shed load and shield equipment during the narrow warning window after alerts arrive from that spacecraft a million miles upstream. If recovery is measured in years, that is not a law imposed by the Sunday. It is the result of choices not yet made, investments not yet committed, and preparations not yet treated as urgent. Here, the frightening part carries an unexpected thread of hope. The word preventable. The storm may come. The catastrophe does not have to follow. The question is whether small storms, including ones like tomorrow's, are treated as free warnings, or whether they are admired as light shows and forgotten by the weekend. So this is the worst case assembled into one picture, a Carrington-scale cloud, of the kind the sun produces once or twice a century, and of the kind it almost sent our way in 2012, arrives with its magnetic field aligned in the most dangerous direction for Earth. The magnetosphere becomes far more exposed. Induced currents pour through continent-spanning wires. Major transformers saturate, overheat, and fail in clusters. Then the grid falls into a darkness made especially difficult to lift because the machines required for restoration have themselves been destroyed. That is the deeper implication behind the beautiful lights you may see tomorrow. The same sun is involved, the same physics, the same family of clouds, only larger, better aimed, and arriving on a schedule we do not control. Yet the storm itself is only part of the reason to be afraid. The other part is our own design. We did not merely leave this danger unguarded. We built the most exposed civilization that has ever existed, and year by year, the exposure grows. It raises a stark question. How much of modern life have we placed inside systems that fail in the very conditions they most need to survive? Part 8. Everything now runs on the two things it breaks. Until now, the focus has stayed close to Earth, transformers, transmission lines, and the grid, because that is where the most severe physical damage could unfold. But a great solar storm does not stop at ground level. Its reach extends upward into the orbital machinery we have wrapped around the planet. Within a single human lifetime, those machines have become woven into daily life in ways earlier generations would scarcely have imagined, and they occupy precisely the environment a solar storm can make dangerous. This is where the story widens. The threat is not only beneath our feet in copper, steel, and substations. It is also above us, in the fragile electronics moving through near-Earth space. Begin with what happens to the upper atmosphere. When a geomagnetic storm deposits energy high above the surface, that region warms. Warmed air expands. Even the extremely thin traces of atmosphere, found a few hundred miles up, where many satellites travel, can swell outward and become denser during a storm. A spacecraft passing through that thicker layer encounters increased drag, a stronger resistance than expected. The effect is a little like a swimmer discovering that the water has become syrup. Motion becomes harder, speed is stolen away, and the orbit sinks lower. This is not only theoretical. A few years ago, during a geomagnetic storm that was nowhere near the worst case, newly launched communication satellites entered atmosphere that had been expanded by storm heating. The added drag pulled dozens of them down before they could reach operational altitude, and they burned up. Dozens were lost in an event that did not even qualify as a great storm. Now place that same process inside a much larger event, and set it against the thousands upon thousands of satellites now circling Earth. The scale of exposure begins to come into view, quietly but unmistakably. Then there are the high-energy electrons, the same population to remember from earlier, the ones that rose to 1,284 units on the 6th of June. When the flux of those fast electrons increases, satellites are not protected simply because they are solid objects in space. The particles can penetrate. They work their way into insulating materials inside the spacecraft and allow static charge to accumulate deep within its structure. Eventually, that hidden charge may release, producing a tiny internal lightning bolt. From the outside, the satellite may look unchanged. Inside, electronics can be damaged or destroyed. Engineers call this internal charging, and it is one of the major ways space weather kills satellites. The phrase sounds technical and almost calm, but the implication is severe. A storm can attack the grid below and the orbital infrastructure above, striking the very systems modern civilization increasingly depends on. To understand, coordinate, and recover from disruption. The figure recorded this week, 1,284, was large enough for an automated warning to sound. In an extreme storm, the region those satellites must cross can become much harsher, and every spacecraft moving through it is, in a sense, risking its electronics against the disturbed space around Earth. The scale of that risk has changed sharply. Compared with even 10 years ago, there is far more hardware overhead. And spaceflight is now passing through the greatest growth in orbital objects it has ever seen. A domain that once held hundreds of working satellites now holds many thousands, with plans reaching toward tens of thousands more. Across low orbit, vast constellations of small spacecraft are being arranged to deliver internet service across the globe. Each satellite is one point in an increasingly essential network, and each point travels through the same environment that a major solar storm can fill with drag, electrical charging, and danger. The simple lesson is quiet but stark. The more we place in orbit, the more we leave exposed. And the new mega constellations are built from small satellites that are deliberately light, inexpensive, and not protected by heavy shielding. That design makes it possible to launch them in enormous numbers. But it can also make them less resilient when storm conditions arrive. So the fragility is no longer only on Earth. We are creating another vulnerable system above us, linking it to the one below, and both are ultimately facing the Sunday. This raises a larger question. How much of modern life now depends on machines moving through a region we cannot make calm? Yet the exposure that may matter most is not always the most visible one. It is timing. When most people hear about satellite navigation systems such as GPS and its relatives, they imagine the familiar blue marker on a map. A severe storm can certainly disrupt that. The disturbed upper atmosphere that increases drag on satellites can also bend and distort navigation signals as they travel through it, blurring their timing, reducing their accuracy, and at times interrupting service over the daylight side of Earth. Losing a map would be frustrating, but it is only the surface of the problem. At their heart, those navigation satellites are not merely tools for position. They are extraordinarily accurate clocks in orbit. Their signals carry time with such precision that a receiver can work out its location from tiny differences in the arrival of those signals. Quietly, that clockwork has been woven into parts of modern civilization that are not about directions at all. Finance relies on precise timing to mark transactions and keep markets aligned to fractions of a second. Telecommunications systems, including cell towers, use it to coordinate their signals. Electrical grids depend on timing to keep distant components working together. Logistics, shipping, data centers, and many other systems lean on a signal descending from satellites that are themselves operating in an environment a great storm can make hostile. In that sense, a damaged navigation signal is not just a problem for travelers. It could send a subtle shock through finance, communications, and the grid, revealing connections to the sun that most people never knew existed. This hidden reliance on satellite timing is one of the more quietly unsettling features of the world we have built, because it did not appear through a single grand decision. It grew almost invisibly. Navigation satellites were first sent up to help determine position, but the time signal they transmitted was so exact and so readily available that engineers across many industries adopted it as a common clock. Stock exchanges use it to timestamp trades to the microsecond, a level that can matter greatly when wealth can shift in the interval between one microsecond and the next, and when regulations require those records to be accurate. Cellular networks use the same timing discipline, so towers can pass a call from one to another without dropping it. Data centers use it so their servers can agree on the time, which may sound minor until globally distributed databases begin to depend on the correct order of events. Some parts of the power grid also use it to keep distant sections synchronized in phase. Without much public attention, a clock in the sky became part of the foundations of finance, communication, computing, and energy at the same time. All of those layers can end up depending on the same small group of satellites, traveling through the same difficult space environment, and outside the engineering communities that maintain these systems, the dependence is nearly invisible. If a great storm weakens that timing signal, the first sign may not look like a satellite failure at all. It may appear as scattered, unrelated problems across countless systems, each one seeming separate, while the common cause lies above in a disturbed sky. That possibility is unnerving, precisely because the connection is so hard to see until it is strained. Added to this is the fastest effect of the flare itself. Its radiation crosses space at the speed of light and strikes Earth's upper atmosphere on the daylight side. High-frequency radio waves, which normally use that region of the atmosphere to bounce beyond the curve of the planet, can suddenly lose that pathway. During a strong flare, high-frequency radio can black out across the entire sunlit half of Earth. This is not an obsolete or decorative technology. Aircraft crossing the great oceans, beyond the reach of ground towers, use it to remain in contact. It also serves as a crucial emergency communication route when other systems have failed. In the harshest moments of such an event, the channel people might expect to rely on in a crisis can be the one the crisis removes first. The timing of that loss matters, because it means the early moments of trouble could also become moments of silence. And then comes the cascade on the ground, the part that is hardest to picture because most of us have never had to live through it at full scale. We tend to imagine a power failure as darkness in the room, a silent refrigerator, and a temporary inconvenience that ends once crews repair the line. But take electricity away from a modern city not for a few hours, but for weeks. And the failures begin to stack in a sequence that is rarely considered. Water stops because the pumps that lift it into towers and push it through pipes require power. After a day or two, taps can run dry and toilets may no longer flush. Fuel becomes difficult to reach because gas station pumps are electric, so generators purchased for exactly this emergency cannot be refueled after their first supply is gone. The trucks that would deliver more fuel face the same problem if they cannot be filled. Food in stores begins to spoil when refrigeration fails. What starts as a blackout becomes something broader and more physical. The systems that normally make a city feel stable begin to reveal how tightly they are bound to electricity. The frightening part is not any single failure by itself, but the way each one can make the next harder to solve. When the power remains absent, food stops arriving for reasons that are quieter than hunger but just as decisive. The supply chains that refill store shelves depend on electric scheduling, refrigerated transport, and fuel pumps that also need electricity. Money, too, becomes strangely unreachable because most of it was never sitting somewhere as paper. It existed as digital entries inside machines that require power and networks to speak to one another. Pharmacies lose the ability to keep insulin cold. Hospitals lean on generators until the fuel is gone. And after that they become darkened buildings filled with patients whose lives were tied to machines. Cell towers fade as their backup batteries drain. This is where the scale matters. If one town goes dark, help can come from the next. But if the affected region is too vast, and the outage lasts longer than ordinary preparation can survive, the event changes character. A blackout is the moment the lights fail. A collapse is what follows when food, medicine, money, hospitals, communications, and fuel all begin failing in sequence, with no simple path back to normal. The dividing line between those two futures may be nothing more dramatic than the storm's size and the fortune of when it strikes. That is why the whole structure we have built deserves to be seen at once. As far back as 1859, the great weakness was already visible. A solar storm could drive damaging currents through long conductors and disturb the environment around Earth. Knowing that, humanity went on to stretch the longest wires ever made across continents, place thousands of satellites overhead, and turn the timing signals from those satellites into the hidden pulse behind finance, communication, and electric power. The concern is not simply that we failed to protect ourselves well enough. More unsettling is the possibility that, year after year, and decade after decade, we arranged civilization into an almost ideal target for the very kind of disturbance we already understood. Every additional satellite, every system that depends on GPS timing, and every mile of grid bound more tightly to another mile makes ordinary life smoother on calm days, while adding another point of exposure when the large storm arrives. Dependence is not shrinking, it is increasing. We rely on these systems more now than we did last year, and the next year is likely to bind us to them even further. The target has not only been constructed, it is still being enlarged, and the direction of that growth is troubling for safety, because modern technology tends to deepen reliance rather than reduce it. We are moving transportation onto the electrical grid, shifting heating toward the same grid, and building data centers that draw power on the scale of small cities. Each of these choices may have admirable reasons behind it. Yet each also concentrates more human activity inside the very system a severe geomagnetic storm can disrupt. Commerce and conversation are being pushed into networks that assume uninterrupted electricity and permanent connectivity. Satellites are being launched faster than at any earlier moment in history. In one sense, this is progress. In another, it is a thicker cord tying survival to systems. A great storm is capable of cutting. A century ago, a Carrington-level event would have encountered a world with relatively little to damage. 50 years ago, it would have met a vulnerable electrical grid, but not a civilization deeply dependent on satellites and precise timing. Today, it would meet the most electrified, interconnected, timing-dependent society that has ever existed. And tomorrow, quite literally, it would meet one slightly more exposed than the one that exists today. We are not merely waiting in place for the sun to remind us of its power. We are walking closer to the hazard while building the target higher, confusing efficiency with security, even though in this one narrow but vital respect they may be opposite. That is the darker implication when stated plainly. The storm approaching tomorrow is not the end of anything. It is a small event, a trickle, perhaps only a display of light. What should disturb us is that this harmless face belongs to a force that can also take a catastrophic form, a force expected on the scale of a human lifetime or less, a force that nearly reached us in 2012, and one against which the modern world has steadily made itself less resilient. The honest word is exposure. We are exposed now, and the trend points towards still greater exposure. Before closing that thought, intellectual honesty requires a second half, because solar storms have gathered a fog of claims around them. When one of these events appears in the news, the online world often fills with dramatic assertions about what the sun can do to Earth. It is worth moving through the largest of those claims carefully, not with ridicule, because the instinct to pay attention to danger can be a healthy one, but with a clean separation between what science supports and what it does not. The genuine risk described here is already serious enough. It does not need embellishment, and exaggeration can make the real hazard easier for careful people to dismiss. One of the most repeated ideas is that geomagnetic storms set off earthquakes or volcanic eruptions. In that version of the story, solar activity somehow energizes the planet, loosening faults and stirring volcanoes into motion. The proof usually offered is a cluster of earthquakes or eruptions occurring near the time of a storm. It is easy to see why that feels persuasive. The timing can appear dramatic, and pattern seeking is a powerful human habit. As this storm approaches, notable volcanic activity is indeed present around the world. A volcano in Alaska is at an elevated alert level. The Great Shield volcano in Hawaii has been producing a striking display, and eruptions are continuing across Indonesia, Russia, and the Philippines. From a distance, the mind may want to join those dots. The sun is restless, the earth is restless, so perhaps one must be driving the other. But here the physics gives a much firmer answer, and precision matters. A geomagnetic storm does couple some energy into Earth's solid body. That part is real. Yet the amount is many, many orders of magnitude smaller than the energies involved in geology. A fault approaching rupture contains strain energy accumulated over decades and centuries as tectonic plates grind slowly against one another. That reservoir is colossal. The heat and pressure behind a volcanic system, with molten rock kilometers below the surface, are also colossal. Against those deep earth processes, the contribution from a geomagnetic storm is not the same kind of actor. The timing may invite suspicion, but timing alone is not a mechanism. In a subject this consequential, that distinction is not a technicality. It is the line between a frightening reality and a story that the evidence does not carry. Set against the force of a thunderstorm, the electromagnetic energy a solar storm can induce in the ground is closer to a faint murmur than a commanding blow. The issue is not that there is no link at all between space weather and Earth's electrical environment. Rather, it is that the link is far too weak to carry the dramatic burden people sometimes place on it. When researchers have searched carefully, using statistics rather than impressions, for a meaningful connection between solar activity and earthquakes or volcanic eruptions, the result has been weak at best and often indistinguishable from nothing. What looks, at first glance, like a suspicious cluster is usually the ordinary pulse of a restless planet. Volcanoes are erupting somewhere, faults are slipping somewhere, and then a solar storm arrives just when everyone is looking upward. In that moment, the timing can feel meaningful. But feeling is not physics. The volcanoes in Alaska and Hawaii and Indonesia are not responding to what the sun happened to do this week. They are moving according to their own internal rhythms, shaped by magma, pressure, and the deep workings of Earth itself. In this case, the overlap in timing is coincidence, not cause. The underlying science does not support the idea that the storm is triggering the eruption, and it would be misleading to pretend otherwise. This matters because the question is not whether two striking events can appear side by side on the calendar. The question is whether there is a mechanism strong enough to connect them. Here we run into a deeper and very human trap. Our minds are remarkably good at finding patterns, and that gift has always helped us make sense of danger. Yet the same talent can mislead us, especially when two vivid or frightening events happen close together. We see a solar storm, then we notice an eruption or an earthquake, and the brain quietly draws a line between them. But Earth is never geologically still. On any given day, dozens of active volcanoes exist around the world, and earthquakes of many sizes are occurring continually, because we live on a planet whose interior remains hot, dynamic, and unsettled. So if someone waits for a solar storm and then scans the globe for seismic or volcanic activity, they will find something. Not because the storm called it into being, but because there is almost always something to find. The storm did not summon the volcano. More likely, the volcano was already doing what volcanoes do, and the storm simply gave observers a reason to notice it. This is one of the most useful habits of thought calm space can encourage. Do not ask only whether two events happened near one another. Ask whether any physical process could plausibly connect them, and then ask whether that proposed connection survives careful comparison with data rather than intuition. On the question of solar storms causing earthquakes or eruptions, that test fails. The proposed mechanism is too feeble, and the serious checks do not reveal the claimed relationship. In a calm examination of the evidence, coincidence remains the better explanation. There is, however, a more refined version of this idea, and it deserves a fairer hearing. Some people point not to solar storms directly, but to faint electrical signals recorded at certain ground stations. Narrow features in the electric field that some researchers have suggested might act as earthquake precursors. This is not the same as pure fantasy. Real scientists are investigating whether Earth may produce subtle electromagnetic signs before a rupture occurs. That possibility is interesting, and it raises a legitimate scientific question. But the essential point is this: the predictive value of such signals has not been established. A brief anomaly at one station is not the same thing as a reliable earthquake forecast. It may be meaningful, or it may be noise, or it may be something whose meaning is not yet understood. The honest state of the field is that earthquakes still cannot be predicted reliably by any known method, electromagnetic or otherwise. So when someone displays a small feature on a spectrogram and declares that an earthquake is imminent, the calm response should be curiosity, not fear. Research into possible signals exists. A dependable forecasting tool does not. Confusing those two categories is where the mistake begins. That distinction is worth slowing down for, because it can easily be misunderstood. To challenge exaggerated claims is not to dismiss the entire field. Careful work is being done on whether large earthquakes may be preceded by detectable changes in electrical or magnetic conditions, in the behavior of the ground, or in gases released from stressed rock. Some of that work may be promising as research. Yet there is an enormous distance between an intriguing signal and a prediction that society could actually use. That distance is not a minor technicality. It is the space where careful science operates. A practical earthquake prediction would need to say where an earthquake will happen, when it will happen, and how large it will be, with enough reliability that people could act on it without being warned so often falsely that they stop listening. Nothing in electromagnetic precursor research has reached anything close to that standard. Responsible researchers in the field are usually very clear about this. The problem is not the study of subtle signals themselves. The problem arises when a single unusual reading from a single instrument is presented as though it were a forecast. That is not how the cautious version of the science speaks. So, it is possible to hold two ideas together without contradiction. The research is real, and it may be worthy of continued attention. But dramatic online predictions built from one isolated blip are not the same thing as science. They are pattern recognition dressed in scientific clothing. The difference matters because it separates investigation from alarm and curiosity from certainty. In astronomy and earth science alike, that discipline is often what keeps wonder from becoming confusion. Then comes another claim, that authorities are concealing the true severity of a solar storm, softening the warnings so the public will not panic. In this case, reality points almost in the opposite direction. The forecasts are public. The watch mentioned earlier is posted openly and can be read freely. The solar wind data, arriving from spacecraft upstream of Earth, is released close to real time. Observatories across many countries are looking at the same sun and working with the same kinds of measurements, which makes any coordinated suppression extraordinarily difficult to imagine. The uncertainty in the forecasts is not a sign that the truth is being hidden. It exists because the truth is physically difficult to know ahead of time, especially when the magnetic orientation cannot be measured until the cloud is nearly upon us. The obstacle is physics, not concealment. If anything, the people who study space weather tend to want the public to take it more seriously, not less. And when the cover-up idea is examined calmly, it becomes an even stranger proposal. Such a secret would require space weather agencies across the world to act in concert, because the United States is not the only country watching the sun. The same star is being observed from many places, by many instruments, under many institutions. That shared visibility does not remove uncertainty, but it does make the idea of a hidden, globally suppressed truth much harder to sustain. Across Europe and Asia, observatories and space weather forecasting centers are operated by separate governments, with separate priorities, and in many cases, with little reason to simply trust one another. Yet, they are all looking at the same sun, measuring the same events, and releasing the same kinds of figures into public view. For a hidden deception to work, the teams running the spacecraft would have to corrupt the very data feeds they publish openly, feeds that thousands of independent researchers and even dedicated amateur space weather watchers retrieve and examine every day. Any obvious manipulation would be noticed quickly because the audience is not passive. It is full of people trained to compare, question, and verify. The conspiracy would also have to include universities, journals, and international research groups, all preserving one secret indefinitely without a single meaningful leak. That kind of machinery does not fit the way large-scale science normally functions. In science, the rewards often go to the person who spots the pattern others missed, not to the person who helps hide it. The simpler truth is less theatrical, but far more useful. The measurements are available, and the people most qualified to read them are not suppressing the warning. They are publishing it in reports, papers, and testimony, often for a public and for institutions that have not fully chosen to pay attention. And this is where the quieter lesson begins, because beneath the weakest versions of these claims, there is a real anxiety that should not be mocked away. The feeling that a severe solar storm could cause serious harm is reasonable. The suspicion that the danger has not been taken seriously enough is also reasonable. The worry that our protections are not yet where they should be is, in many ways, justified. The electrical grid is genuinely exposed to geomagnetically induced currents. The effort to strengthen it, to install equipment that can keep those currents away from enormous transformers, to build deeper stocks of spare parts, and to prepare for extreme conditions remains unfinished. The risk is real, but its center is not volcanoes, and it is not earthquakes. It is the grid, the satellites, the cables, the timing systems in orbit, the ordinary, unromantic infrastructure that allows modern life to feel effortless. That may be the most unsettling part. The reality is less mystical than the fantasy, yet more disturbing, because it points towards something we could work on, and in many cases, still have not. So let us bring the picture back down to Earth. Tomorrow, late in the day, a cloud of plasma that left the Sun on the 6th of June is expected to reach our planet. If its magnetic fields arrive in the wrong alignment, the disturbance may rise to the strong level that forecasters have described. Under a clear northern sky, some observers could see auroras pushed farther south than usual, into places where such lights are rare. It may be one of the most beautiful sights a person ever sees. And for most people, the lights at home will remain lit. Phones will still function. Grid operators will handle the small flow of induced current in the ways they have learned to manage. By the following day, the event will probably have faded into memory, along with a handful of striking photographs. That is, almost certainly, the version of tomorrow we should expect. This is not a warning to fear that day. It is a reminder that tomorrow may be the gentle rehearsal for a harder examination that will eventually arrive. The sun demonstrated its power in 1859. It offered another reminder in 2012, when it released a dangerous blast that missed Earth by about a week. The same physics that lays color across the polar sky can, under different conditions, bring down the electrical grid. What changes are the storm's size, which we cannot command, the direction of its magnetic field, which cannot be known with confidence until the event is almost upon us, and the timing of the sun's rotation, which is left to chance. The rest belongs to us. The wires we have stretched across continents, the satellites we have placed above the planet, the dependencies we have created, the spare equipment we have not sufficiently stored, and the hardening we have postponed. These are human decisions. They are not mysteries of the heavens. They are choices made here, beneath the sky. 93 million miles away, a star gives Earth its light, its warmth, and the energy that sustains every living thing on this planet. It has done so reliably for billions of years. But at intervals set by its own nature, with no concern for human schedules. It erupts and sends part of itself outward through space. Tomorrow, the piece that reaches us is expected to be small. At some future point, on a timescale no one can honestly guarantee is distant, a much larger one will come. When it does, it may encounter a civilization that has tied nearly everything it does to the very system such a storm can damage, while leaving itself, year after year, more exposed rather than less. The auroras tomorrow night may be lovely. If the sky is clear, and you are far enough north, look up. But know what you are seeing. It is the calm face of a natural force that, in a single day, could take apart much of the modern world's working machinery. The question that should trouble us is not whether such an event will arrive. It is whether, when it finally does, we will have prepared in any meaningful way, or whether we will have continued building the target until the morning when the lights no longer return.